All right, in this lecture, we're going to talk about torsion of round cross-section bars. And this will be a new section. We'll call this section 4. Torsion is common in power transmission and in drilling and other similar sorts of situations. So let me write a little bit of this down. You see power transmission shafts in cars, power plants, and so forth. And you're probably familiar with torsion through statics, and you probably drew this as curly arrows acting on a bar. So here's a round bar. I'm going to put a torque on this side, and for equilibrium, we'll have an equal and opposite torque going around the other way on the other side. Now, a notation that I like to use in this class is a double-headed arrow notation for torque. And the way that works is if you use the right-hand rule and your fingers curl around in the direction that the torque does, your thumb will point in the direction of this double-headed arrow. And so there's a picture of this right-hand rule. Okay, so this would be equivalent to a double-headed arrow going out to the right in this picture. Now, you can apply torsion to any kind of cross-section, but in AEM 250, we're only going to look at torsion of circular cross-sections. In other classes, if you're in mechanical engineering, you'll take machine design. If you're in civil engineering, you might take steel structural design. And in aerospace engineering, you have aircraft structures. You'll take a look at other shapes. Such as rectangular sections, maybe ovals, I-beams, T-shaped cross sections, all these other kind of shapes you can do torsion on, but we're only going to study torsion of circular sections in this class. Now, the goal of our discussion today is we want to know what kind of stresses and what kind of deformation that we can have in bars that have torsion applied to them. Kind of like we started out beginning of the semester with stress, axial stress, and a bar in tension is force divided by area. We want to come up with some kind of formula to tell us what the shearing stress is in a bar when we have it subjected to torque. To do this, we're going to take a look at some observations of elastic deformation. And so let's make a list of these observations. The first one is that plane cross sections remain plane after loading. And I've copied this picture out of our book. It's on page 238, it's figure 4.2. And on the top of this picture, what we see is a bar up at the top that has a circular cross section before any torsion is applied to it. And the next picture is the same cross section bar, but with a torque applied to it. You can see these lines, they kind of curve. They form kind of a helical pattern as they go from one end to the other. But what we're talking about is the cross section. And when I say plane cross sections remain plane, if we look at a cross section, that's one of these vertical lines that they drew on the bar before it was loaded, see how it's straight up and down. And after that torque is applied for the circular cross section, that cross-section still stays straight up and down. It stays flat and plane. In contrast, for bars that have non-circular cross-sections, you can have some warping. And so here's a bar that has a square cross-section on the bottom. Before it's loaded, these cross-section planes are straight up and down. But after it's loaded, notice that it kind of hooks over. Try to exaggerate that a little bit. But right here and right here at the corners, it kind of goes a little bit to the left on the top and a little bit to the right on the bottom of this corner. That's out of plane warping, and that kind of makes the situation a little bit more difficult to analyze. So we're going to leave that for other classes. In an AEM 250, we're only going to study torsion of circular cross-section bars. Okay, so let me just write down a couple notes. These things stay flat. No warping and no tilting. And this is for circular cross-section bars. A couple of other observations that we can make is that when we have pure torsion on a bar, the bar does not get any longer. The fancy word for this is the bar is inextensible. Now that also means that we don't have any axial strain when we have a circular cross-section bar in torsion. Okay, a third observation is that all points on the cross-section move through the same angle of twist. So what I mean by that is, let's see if I can draw the cross-section. It's a circular cross-section, and we have the center of that circle, and we have a couple of points on the edge, maybe point A and B. When we apply a torque to this cross-section, the original line from A to B was straight up and down, but if I put a torque this way, then this line is going to move to this new position. And let me draw that a little bit better. I want to try to go through the middle of the circle. So this would be the new location of point A, and this would be the new location of point B. And the angle that's formed from where it used to be to where it is now, that's called the angle of twist, and we're going to use the symbol phi for that angle. So any point that lies from A to B still moves on that line from A star to B star. All of those points move through the same angle of twist. And this not only holds for this one line that I drew in here, but it holds for any line that you can imagine passing through the center of this cross-section. All right, so with an end goal of wanting to find out what the stress is in a bar in torsion, we're going to start off with first figuring out what the strains are in the bar in torsion. Then we're going to use Hooke's law to relate stresses and strains. So I want to talk about the deformation of a bar, and this is related to some figures that you'll see in our book on page 239 and 240. I've copied one of them over here. I use a little bit different symbols and letters than the book does, but I wanted you to see my picture, and I wanted you to see the picture similar to the one that's in the book. So what I have on the left is a bar that's fixed on the left side, and I have point A identified on there, and I have the axis of the bar going down through the center of that shaft, and then I have point B that I've identified over on the right-hand side. What I'm going to do is I'm going to apply a torque to this. If I look at the end view, okay, there's my point B before the torque is applied. And when I apply this torque in this direction, point B is going to rotate to some new location. I'm going to call that B star. And this angle is our angle of twist again. That's our angle phi. Now point A doesn't move because it's on the fixed side, but point B does. So here it is on the 3D picture. So this will be my B star. It's kind of like this in this picture, A to B, and they call their endpoint F, and then it twists and goes to F star. The same idea from that picture. So let's see if I can draw this somewhat straight. It'll be kind of hard to do on this tablet that I have. So I'll just do it freehand the best I can. Okay, so originally there was a straight line that went from A straight across to B, but now it's turned a little bit. It's rotated. And in this picture, what we have, if the length of the beam is L, the length of the bar, then we would say that at the end, x equal to L, it has a twist of phi of L. That would be the twist at point B in my picture. And if we have a coordinate system over on the left side going to the right, you can see that the angle of twist varies from 0 on the left side to this phi sub L over on the right side. And it varies linearly with this distance x. So if I'm halfway along the length of this bar, then I have half as much angle of twist. So we have one coordinate system here going down the axis of the bar. That's the x direction. The other coordinate system that we'll use is a polar coordinate system from the center of the bar out to any particular point on the cross section. We're going to call that distance rho. If the diameter of the bar is 2 capital R, then rho will equal to R on the outside edge. Now this is kind of a special case where the left side is fixed and the right side is free. In general, we might be interested in a section of the bar that's somewhere in between. And so we're going to take a look at a piece of this of length delta x. And not only a piece of length delta x, but we're going to look at a core inside of this bar. And what I mean by that is a small piece that's inside of this larger piece. And here I've shown it in blue, both in the 3D view and on the end view. Okay, so I'm going to look at this in a similar way that I did for the full structure. And I'm going to draw that down right below here. Before that bar is loaded, just like we had A and B on the left and right side of my large structure, I'm going to identify a couple points, points C and D, on the left and right side of this small core. So the length of that is delta x. This will be before the torque is applied. Now, after the torque is applied, both of these points are going to rotate some because C is not on the fixed end. me redraw this little section. And C goes to C star, D goes to D star. Now, I want to draw a line straight across, and I'm going to call this point D double prime. Okay. And the line from C star to D star, I'm going to draw in there as well. The angle of twist over at this position is going to be phi of x, okay, because it's the distance from the fixed end to the left side. And we go over a little bit further to get to x plus delta x. So the angle of twist over on this end is phi of x plus delta x. That's the angle of twist at position D. The angle that I'm showing on the end, it's kind of hard to draw that in there, but that angle on the end I'm going to call delta phi. That's the relative angle of twist. So that is phi of x plus delta x minus phi of x. All right, so let me redraw these pictures so I have them on this page. So before the load is applied, points C and D are straight across from one another. After the load is applied, both points C and D rotate. D rotates a little bit more. It goes to D star. C goes to C star. And straight across from C star is my new point. It's a fictitious point I'm going to call D double prime. And I'm going to draw one more picture as if I'm looking at the side view of this picture, straight up the edge of the bar and over. That makes a right triangle, or pi over 2 radians. And I can do the same thing. If I look at this picture, straight up to C star and over to D double prime is a right angle. And then we have a little bit, I'm exaggerating here, we have a little bit of an angle change, so that when we go from C star to D star, we have a change from pi over 2 radians. That change from pi over 2 radians is the shearing strain gamma. So this is how we get a relation with our shearing strain. On the end view of this bar, I have to draw the cross-section kind of big over here. This is the core, so the distance from the center of the bar to that outside edge, that's the distance rho, and that's variable distance. It could be anywhere from 0 all the way out to the radius of the bar. This D double prime is sitting here in this picture, and this D star is over here in this picture. And then that angle we said before was delta phi. Let's look at this triangle. If I wanted to find the shearing strain gamma, I could take the tangent of gamma, and that would be equal to the opposite side over the adjacent side of this triangle. So that would be the distance D star D double prime over the distance C star D double prime. Well, the distance on the top is the distance delta x. So that's the length of this segment. Okay, that's the denominator of this picture. The distance d double prime to d star, we're going to approximate that as this arc length. And so that's going to be rho times delta phi. Now I know that this distance as an arc length is not the same as a straight vertical distance, but if we look over a very small distance delta x and the angle delta phi doesn't change very much, this is a very good approximation. Most engineering materials will have very small strains and they'll break before the strains get very large. So another approximation we can make is that for small strains, gamma, talking about something like 10 to the minus 6, 10 to the minus 3 range, that the tangent of gamma is approximately equal to gamma. So we're going to write down that gamma is equal to rho times delta phi by delta x. We know what delta phi is, so we'll write this one more time. It's phi of x plus delta x minus phi of x divided by delta x. If we take the limit as delta x goes to 0, then we can get the strain at a point. And in the limit, this is the definition of a derivative. So in other words, what we're saying is the shearing strain gamma is equal to the distance from the center of the bar to wherever we want to look at, that's the distance rho, times this thing called d phi by dx. d phi by dx is the twist rate in the bar. And it usually would be expressed in radians per inch or radians per millimeter along the length of the bar. If you have a bar with a constant cross-section with a constant load, that twist rate will be constant. Okay, so let's write that equation down on this page. Gamma is equal to rho times that twist rate. The twist rate's a constant for the problem we're looking at so far. Rho is the polar coordinate variable on the cross-section that varies from the center of the bar to the outside radius, 0 to r. And if we notice, rho is to the first power. If you put all this together, what that means is that we have a shearing strain distribution that varies linearly with distance from the center of the bar. So let's write that down. If I were to look at an end view of a circular cross-section, it's hard to draw real good circles, but if I were to look at one radial line going from 0 to r, I can indicate the shearing strain distribution as a triangle like this, where this picture would hold for any radial line that goes through this cross-section. Well, that tells me then, just by looking at this picture, that the maximum shearing strain is on the outside edge of my bar. I have 0 shearing strain at the center of the bar, and then I have this linear variation in between. We could also do the same thing with a hollow bar that's a circular cross-section. Okay, just trying to do my best to draw a circle. Now, the shearing strains and shearing stresses are similar in the fact that you have to have two surfaces that want to slide past each other in order to generate those shearing stresses and shearing strains. So what that means is inside the circle that's hollow, we don't have any shearing strain. But the strain distribution still varies linearly with that distance. What that means is for this radial line, I start to pick up strain on the inside edge of this cross section, and it varies linearly with distance to the outside edge. Okay, so here the maximum shearing strain would be equal to R times the twist rate. Here, gamma maximum is equal to the outside radius times the twist rate, and the minimum is equal to the inside radius times the twist rate. So just by that analysis, I know where my largest shearing strains are going to be for a bar in torsion. We'll later see that the shearing stresses will be related directly to the shearing strains through Hooke's law. So the biggest shearing stresses will be on the outside edge of a bar in torsion. Let's do that now. Hooke's law on shear is tau is equal to G gamma. So now I know that the shearing stress is dependent on the twist rate and the distance from the center of the bar. All right, and here's some nicer pictures. Now they're showing the shearing strain distribution in these pictures, but again, you just multiply that by the shear modulus in order to get the shearing stress. I'll give you a hint. On your test, number 2, I'll often ask you for this shearing stress distribution. And so if you have a circular bar, you would sketch this picture showing a linear variation of shearing stress with that distance. If you have the hollow bar, your picture would look like this. Now, I'll caution you too that I'm a little bit particular about these pictures. Notice in this picture we don't have any arrows in here because there's no material. We can't transmit any shearing stress. Sometimes I'll see people that get a little sloppy with these pictures, and I'll show you how not to do it. I usually don't like to talk about how not to do things, but sometimes I'll see pictures like this. Okay, I won't give you credit for that picture because it's indicating stresses where there is no material. So try to scale your picture reasonably well so that it looks like the stress arrows stop at the edge of the bar. Hope that makes sense. We'll talk about this a little bit in class as well. All right, so let's take a look at equilibrium. Right now what we have is an equation that says that our shearing stress tau is equal to G times rho times this twist rate. The problem with this equation is that this twist rate is kind of hard to measure. And what we really want is a formula kind of like sigma is equal to F over A that tells us what our stress is in terms of load. Here we don't have load in here yet. The way that we're going to incorporate load into this equation is by looking at equilibrium. Let me see if I can draw a circle. And we've actually done something like this already this semester. Here we have the center of our bar, and I'm going to take a look at a small piece of area that I'm going to call dA. And on that dA is some shearing stress tau. If I take that tau and I multiply it by that dA, I get a little bit of force at that particular point. And so that dF is going to be equal to tau times dA. If I want a little bit of torque, I will take that force times the moment arm distance. So the torque, contribution to the torque dt, is going to be equal to rho times dF. It's going to be equal to rho times tau dA. And if I want the total torque, then I would integrate both sides. And on the right-hand side, I would have an area integral of rho times tau times dA. Rho is not a constant, and neither is tau. Tau depends on this equation. So let's plug that in here. And we can simplify this a little bit because now some things are constant. The shear modulus would be constant if we have all one material. And the twist rate does not depend on the cross-section dimensions. So it is also constant. It can be pulled out in front. And now we're left with an area integral of rho squared dA. Now you may have seen this, something similar to this, maybe in a statics class or and maybe even in calculus when you talked about moments of inertia. The terms in this integral have nothing to do with the material properties or the stresses. It only has to do with the distribution of the area of the cross-section away from the center of the cross-section. This is called a moment of inertia. And because it's about a polar axis, in other words, an axis that's coming out of the page at us, it's called a polar moment of inertia, I sub p. Now, typically in a calculus class, you would derive this formula. We don't have to derive that formula in this class. I'm gonna write it down, and actually it's in the appendix or the back cover of your textbook. The polar moment of inertia for a solid circular cross-section is pi over 32 diameter to the fourth. If you have a hollow section, then the polar moment of inertia is pi over 32 outside diameter to the fourth minus pi over 32 inside diameter to the fourth. Notice that this would have a dimension of length to the fourth power. If you want, you can kind of group these together and make it pi over 32 outside diameter to the fourth minus the inside diameter to the fourth. Be careful. Make sure that you take these numbers to the fourth power before you subtract them. All right, so let's write down what we have from our previous page. We said that the torque now would be equal to G times the twist rate times this integral that we're going to call I sub p. The other thing that we know from a few pages ago is that the shearing stress is equal to G times the twist rate times rho. I can solve both of these for the twist rate and eliminate that twist rate term. So from this one, d phi by dx is equal to the torque divided by I sub p g. And from this equation, d phi by dx is going to be equal to the shearing stress divided by g and rho. I'm going to set these equal to each other. Notice the g cancels out. I can solve for the shearing stress, and it says that the shearing stress for a bar in torsion is equal to the torque times the distance from the center of the bar, rho, divided by the polar moment of inertia of the cross-section. This will be a formula that I will guarantee you will use on your next exam. Okay, so it's pretty straightforward. If you have a bar, you do your statics or whatever it takes to determine your torque that's on the bar. Here I am using my double-headed arrow notation. And let's make up some numbers. Say this is 200 inch-pounds for our torque. And let's use a 2-inch diameter bar. Okay, if it's a solid bar, my polar moment of inertia would be pi over 32, 2 to the 4th power. And depending on where I want to calculate the stress at, it would vary from 0 at the center of the bar out to some maximum value of stress on the outside edge. Let's find the maximum stress in this particular bar. We would take our torque, 200 inch-pounds, times the outside radius, 2 inches divided by 2, divided by our polar moment of inertia, pi over 32, 2 to the 4th power. And that will give us some number in PSI. Now there's one more thing that we can do, and we can actually calculate now our angle of twist. On the previous page, we had an equation that said that our twist rate, d phi by dx, was equal to the torque divided by I sub pg. We can separate this and integrate both sides and have phi being an integral along the length of the bar of t over I sub pg dx. The units that come out of this angle of twist formula would be radians. Now, in the previous chapter, we also had some problems where we had an integral for the deformation of a bar. You remember that one? Integral along length of the bar f over AE dx. The phi formula, the angle of twist formula, works in the same way as this little e formula. If the torque changes, if the diameter changes, or the material properties change, all those have to stay inside the integral. But if any of those are constant, they can be pulled out in front. All right. So let's look at that integral again. If t, I sub b, and g are constant, those can be pulled out in front of the integral. We just have an integral of dx from 0 to L, and that would evaluate out to be TL over I sub pg. This looks a lot like our formula for axial deformation FL over AE. We have a load and a length on the top. We have something to do with the cross-section dimensions on the bottom, and we have material property on the bottom as well. Okay, phi is equal to TL over I sub PG. I will guarantee you will use this equation on your exam number 2. All right, so that's all we're going to talk about on this video. In class, we will go through a couple of examples on how to use these formulas.